Hello, this is Nicholas, and by popular demand, I will be doing a calculus review for probably just chapter 1 and kind of some of the exercises. So I'm just gonna start with what I've been asked the most. Apparently, inverting functions is something that maybe needs to be worked on. So, what is an inverse function? It's a function such that f of f inverse of x is equal to x, or f inverse of f of x is equal to x, and this f inverse of x does not equal, don't make this mistake, does not equal 1 over f of x. If you want to write that you're taking a function and raising it to the -1 power, just write f of x to the -1. Okay, and so what you do when you invert a function is you reflect it over the line y equals x, and so you can kind of think of that when you change your x and y variables. So probably for a simple example, I guess, if you've got y is equal to x plus 2, then what you're going to do is you're going to switch your x and y variables, which reflects it over the line y equals x. And then you're just going to want to solve for y, so y is equal to x minus 2. And if you imagine these graphed, right, you've got one line with a slope of 1 intersecting at this point 2 here, and this is rough, but approximately. And then you've got one line with the slope of 1 and y-intercept of -2, and the line y equals x is right here, so you can see that they're reflected about each other. Okay, so 34 was this. Immediately you kind of want to note that f of x is really just y. It's a function of y. So switch your x and y variables, and that reflects it over the line y equals x. So 2x is equal to natural log of, or x is equal to 2y plus natural log of y. And now you want to note, so normally people kind of get hung up in the fact that, well, first I have to solve for the actual inverse function, in terms of y. But in 34, that isn't the case, right? They just want you to find a particular number within that inverse function. You don't actually need to solve for the inverse function itself, which a lot of people have told me they have tried to do and hasn't been working. So you don't need to. They just are asking for a number. They're just asking for, they want they want f inverse of 2. So just let x be 2. And don't get tripped up, because although you still have you've switched your x and y variables, and you might be tempted to plug in 2 for y, since there's 2 y's and 1 x's, but your x is still your variable that you plug into. You just, now you're still looking for y, just like you were before. So we're gonna let x be equal to 2. So 2 is equal to 2y plus the natural log of y. And I see a 2 here and I see a 2 here, so I'm going to divide by 2. So I get 1 is equal to 1 plus the natural log, 1/2, the natural log of y, 1/2. I can, well, here, I'll make this a little nicer, I guess. 1 is equal to 1 plus the natural log. And now I'm going to move this 1/2 as a power onto this term, and I'll go into Logarithm Properties. So y to the 1/2 is really just the square root of y. Now I can just kind of look at this equation and say, well, y is 0, right? Or y is 1, because the natural log of 1 is 0. So you get 1 equals 1 if y equals 1. So that's your answer, 1. F inverse of 2 is 1. So 35, the one right after it in the book, this one you do have to actually solve for in terms of y after you reflect over y equals x. So f of x is equal to x plus 1 over 2x plus 1. So just kind of replace this with y. And then so when we invert it, what we're going to do is we're going to get x is equal to y plus 1 over 2y plus 1. Now I'm going to multiply by 2y plus 1 to get, oh, I probably should. No, you guys can still see. Okay. X times 2y plus 1 is equal to y plus 1. Now I need to move over. So I'm going to distribute that out. Will I? Yeah, sure. 2xy plus x is equal to y plus 1. I'll just show everything. Now I'm gonna, the idea is that I wanna bring this y over here and bring this x over there so that I can solve for y. So I'm gonna do that. 2xy minus y is equal to negative x plus 1. I'm gonna pull out a y, so y times, right, there's a y here, there's a y there, 2x minus 1 is equal to negative x plus 1. And then just divide both sides by 2x minus 1. So y is equal to negative x plus 1 over 2x minus 1. And if you want, you can replace this y with f inverse of x. And so that is the answer for 35. Let's see. What other ones have I been? Oh, 39. People have been kind of stumped on this one with inverting. So 39. You've got the function, you've got p of t is equal to 100,000. That's kind of annoying. Over 100 plus 900 e to the minus t. Don't let the 100,000 or 100 or 900 intimidate you. The constants are really easy to deal with. It's the ones that have variables that just kind of require a little bit more thought, but not all that much. Okay. I know this is in terms of t, but it really doesn't matter what variable you use. So I'm gonna make this p of x, and I'm gonna make this an x, only because I think it might just help you when you switch your x and y variables, just for consistency's sake, I guess. So p of x, that's really just y, right? So now we're gonna switch x and y. So x is equal to 100,000 over 100 plus 900 e to the minus y, and we need to solve for this y. So I'm gonna multiply both sides by what? 1 over 100,000. In other words, just get this on the denominator. So x over 100,000 is equal to 1 over 100 plus 900 e to the negative y. I'm going to raise both sides to the negative 1 power, because then I can have this y at least as an exponent on the numerator, right? It's even worse if it's on the denominator. So if you raise this to the negative 1, this just brings this over here and that over there. I guess I'll show that real quick. If you've got a over b, where there are really any real numbers, to the negative 1, oh, and b can't be 0, to the negative 1. So what does this mean? I mean, I'm not even really sure how to write this without just writing b over a, but you have 1 over a over b, right? That's what, if you have x to the negative 1, it's equal to 1 over x. So if that doesn't make sense to you, just let x equal a over b. So 1 over a over b is b over a. Okay, so when you raise that to the negative 1, it just switches the variables. So, or the constant in the variable. So 1,000 over x is equal to 100. Oh, I don't think you're gonna be. Here, I'll move it over a little. Plus 900 e to the negative y. Okay. Hello again. I'm sorry I had to go, but now I'm back. So, okay. We're at 100 or 100,000 over x equal to 100 plus 900 e to the minus y. So I'm gonna just subtract 100. So 100,000 over x minus 100 is equal to 900 e to the negative y. Just divide both sides by 900. So you really, when you divide both sides by 900, right, you're gonna have a 900 here, you're gonna have a 900 here, and that's gonna go away. And you can kind of do this because this is really just some power of 10 with place value. You can just 0, that 0 goes away, that 0 goes away, and that 0 goes away. And 100 over 900 is just a ninth. So you get 1,000 over 9x minus a ninth is equal to e to the negative y, which implies that, we're almost done, that the negative of the natural log of 1,000 over 9x minus a ninth is equal to y, and that's our answer. So what did I do there? So if you have e to the y is equal to x, then y is equal to the natural log of x. You know, I just took the natural log of both sides, and then since this you get a negative y out front, I just moved it over to the other side, just multiplied by -1 basically. So that's your answer there. Okay. I guess I should kind of go into natural log since I've been kind of dancing around those a little bit. So natural log properties, or just log properties, natural log. If you don't remember, a natural log of x is really just log base e of x. So that's why when you plug in natural log of e, you get 1, because a logarithm is defined like this. Log base a of b is equal to c if and only if, and that's what the 2f's means, that's what the 2f means, if and only if a to the c is equal to b. So as a kind of example, log base 2 of 8 is equal to 3 because 2 cubed is equal to 8. Okay, so log properties, log base a, and a is just any base greater than 1, right? Your base can't be 1 because 1 to any power is still 1. So anyway, log base a of b, that's a b, I swear, plus log base a of c is equal to log base a of bc. So in other words, the sum of two logs is the log of the product of the inputs. As an example, if you have log, and also if your textbook, if this textbook just uses, if they just write like, say for example, log 250, then that implies that it's base 10. You normally, if you see a log and you don't see a base, it's base 10. That's just kind of assumed. Sometimes people will assume it to be natural log, but they use ln in our textbook. So if you see log without the base, it's 10. So log base 10 of 250 plus log base 10, and I really don't even need to write the 10 of 4, for example, is log base 10 of 1,000, right? 250 times 4, which is equal to 3 because 10 cubed is 1,000. Okay, so what's another property? Log, this is very similar to the other one, log base a of b minus log base a of c, and I'm hoping at least that you can guess what this already is. It's log base a of b over c. In other words, the differences of two logs is the log of their division. I guess you could say it as the log of their divisor, or something like that. But that's what that says. So what's a good example of that? well, you can come up with an example of that. I mean, I did one for the other one. And the last kind of immediate property, I guess, that you need to know is if you have log base a of b to some power p, and this is equal to p to the log base a of b. And that's a very, very, very important property. It says that if you have an exponent within the input of the natural logarithm, you can move it out front as a constant. And the same thing, right? If you have it in this form, then you can just move it here. Now, this is important. This is not equal to log base a of b all to the p, right? It's not equal to that. It's all you put the power within the input, not as a power to the whole logarithm. And basically, the reason why this is true, I'm not gonna write out a full proof because I don't want to bore you to death. But the reason why this is true is basically it just comes down to the fact, within the proof at least, that not even e. If you have a is some constant, a to the b, a to the bc, right? And that's really equal to a. Oh, what did I do here? Oh, I'm sorry, I messed this up. If you have a to the b plus c power, right? A to the b plus c power, a c? No. Then that's equal to a to the b times a to the c. And that's kind of where this property comes from. And the other corresponding property for this one is where that kind of comes from. Okay, so... Oh, also, I was just looking at, this is one of the other exercises in the book. This is 36A, and this is going to be a very, very important property for you to know. It was to simplify e to the 2 natural log of 3 power. Okay. So, what is this? This is equal to e equal to, get it? This is equal to e to the natural log of 3 squared, right? Because if you imagine if you had it this form, right, then a power to a power is just, right? I guess I should write it out since I'm trying to do a review. I don't want to skip over too much. If you have a to the b raised to the c, when you have a power to power, you just multiply the powers, so that's equal to a to the bc. That's also an important property you should know, but I think you know that, or at least I hope. So e to the natural log of 3 squared. This is 3 and then squared, which is 9. So in general, e to the natural log of x is equal to x, or probably perhaps more in general, a to the log base a of x is equal to x. And since you have this squared out here, you square it. Okay. Okay. I'm just gonna go through the true and false because I've been asked pretty much every one. So let's do that. Okay, I'm at the true and false now, right on the chapter 1 review, just for the homework. So the first one, if f is a function, then f of s plus t is equal to f of s plus f of t. That is absolutely false. So f of s plus t does not equal f of s plus f of t. Maybe a little challenge for you, if anyone is even watching this far, is try to find a function that actually does exhibit this property. It says give an example that contradicts the statement, so I guess my example would be f of x is equal to x squared, right? Then what you get is, okay, so you plug in s plus t in for x, so you get s plus t, right? Because you let s plus t be x, squared. And then what we're claiming, so I'll just kind of draw a little question mark, is that that's equal to, now you plug in s for x, so s squared, plus, now you plug in t for x, t squared. And hopefully you see that this is not true already, but I'm going to square it out. So s plus t quantity squared is s squared plus 2st plus t squared. It is not s squared plus t squared. I really hope you aren't making that mistake. So, right, if you subtract s squared and t squared from both sides, this, and this goes away, and you get 2st is equal to 0. So basically, the only way that this can happen is if you have the identity function. In other words, f of x is equal to 0. That is one function that exhibits that property, but of course it's not all that interesting of a function. If f of s is equal to f of t, then s is equal to t. Well, no. Okay. F of s is equal to f of t implies, and it does not imply, s is equal to t. For example, pick any function f of x is equal to c, where c is any number. For example, f of x is equal to 3. Then you'll get, so okay, let's plug in f of 2, right? F of 2 is 3, f of 3 is 3, f of anything is 3. So let's say f of 2, right, that's equal to 3, and f of 4, that's equal to 3. But obviously, 2 does not equal 4, so that property is false. My challenge, again, if you're watching this far, is come up with a function that does do that. Okay, number 3, if f is a function, then f of 3x is equal to 3 times f of x. This is, again, false in general. Here, my example again, I guess since I used x squared, why don't I use x squared again? Then, okay, this is kind of where a lot of people mess up. So, if we want to plug in f of 3x into here, right, we let x be 3x. So, f of 3x is 3x quantity squared. It's not 3x squared. It's not 3x squared. It's 3x quantity squared. And the difference is that you square the 3 and you square the x in here versus this other one where you just squared the x. So 3x quantity squared is equal to 9x squared. But 3 times f of x is equal to 3x squared, right? 3 times and then x squared. So, and these two obviously are not equal to each other in general. At 0 they are, but you know, that's about it. Okay, if x sub 1 is less than x sub 2 and f is a decreasing function, then f of x sub 1 is greater than f of x sub 2. Well, yeah, that's true. You can just kind of plug in numbers for that and see that that's true. Just let like x1 be, say, oh, I don't know, -3, x sub 2 be -2, and then maybe your function is f of x is equal to -x, since that's a decreasing function, and you can see for yourself that that's true. Okay. Number 5, if f and g are functions, then f of g of x is equal to g of f of x. Maybe some of you guys don't know. F, and then this is kind of the notation they use. It's like an open circle. F of g of x, that's what that means. That's equal to, and you need to know this notation because for some reason they don't like using this notation in the book. I don't know why. I think it's a lot nicer, but anyway, this is equal to that. You need and make sure you know that that's composition of functions. And what does f of g of x even mean? So it means you've got a function f of x, you got a function g of x, you're plugging in g of x, whatever g of x is defined to be, as the input for f, and then evaluating f. Okay. And g of f, so that's equal to g of f of x. Okay, and this is, again, in general false. What's a good example of this? Well, I don't know. Let's see. Let's use f of x. F of x is equal to x squared, and let's just let g of x be equal to x. I'm just spitballing numbers here. So, g of x. Okay, let's evaluate f of g of x first. F of g of x. What is g of x? Well, it's x. So f of x, and what is f of x? Well, it's x squared. Okay, now g of f of x is equal to, okay, what's f of x? G of x squared. Okay, I gave an example that worked. Oh, yeah. It's equal to x squared. But just come up with, you'll see that. Of course, the one example I used worked. But that is in general false. You can fool around with the functions if you'd like. Number 6 is, if f is 1 to 1, then f inverse of x is equal to 1 over x. No, it is not, and I said that up there. It's not as false. When solving an equation, it is always this is number 7. When solving an equation, it is always mathematically permissible to divide both sides by e to the x. Okay, well, let's just kind of think about this for a second. When is it not permissible to divide an equation? When you're solving an equation, what can't you divide by, right? Okay. I'm sure you know that you can divide by a bunch of different numbers and a bunch of different constants. Okay, but the one number that you can't divide by, well, for your sake, the one number that you guys can't divide by, just for, there's more, but for the sake of this review, is 0. Right, when you divide by 0, the division by 0 is undefined. So, for example, 2 over 0, that's undefined. And the reason why that is because what this is asking, 2 over 0, what 2 over 0 is asking is, how many times can you take away 0 from 2 and be left with 0? So, one more time. How many times can you take away 0 from 2 and be left with 0? Well, that's impossible, right? And whether you subtract, whether you do 2 minus 0, 2 minus 0 minus 0, 2 minus 0 minus 0 minus 0 minus 0 minus 0 minus 0, you're still going to have 2. You're never going to get to 0. So, in other words, this is undefined because there is no number that works. You're always going to have 2. So, this is undefined. And I guess I should bring up that, because you're going to be dealing with this a lot in calculus, especially when we get to limits, which is, I think, next, I don't know. 0 over 0, well, what is 0 over 0? It's known as one of the, I think, 7 indeterminate forms. And why is it indeterminate? Well, okay, think about it again. 0 over 0 means how many times can I take away 0 from 0 and still be left with 0? How many times can I take away 0 from 0 and still be left with 0? Well, as many or as little times as you want, right? 0 is equal to 0, 0 minus 0 is equal to 0, 0 minus 0 minus 0 minus 0 is equal to 0. So in other words, 0 over 0 can be whatever you want it to be. So we call it indeterminate because you are unable to determine a specified answer. So that's important to know. 0 over 0 is indeterminate. But 0 over 2, right, that's just 0. That's just asking how many times can you take away 2 from 0 and be left with 0? Well, 0 times, right? You don't take away 2 at all, and you already get 0 is equal to 0. Okay, enough zeros. So now back to the question. Is it always mathematically permissible to divide both sides by e to the x? Well, it would only be permissible to not divide it, or it would only not be permissible to divide by e to the x if e to the x equals 0, right? But this has no solution in both the reals and the complexes. You can actually get e to the x to be a negative number if you plug in complex x's, but that's beyond the point. For all real numbers, right, e to the x is always greater than 0. In other words, exponentiation always gives a positive number, and if you imagine the graph of e to the x, it's something like, right, it goes up like that, but it asymptotes at 0. It never touches 0 though. So number 7 is true. You can always divide both sides by e to the x because e to the x is always greater than 0. Okay, that was very long-winded. Wow. Number 8. If a is somewhere between 0 and b, then the natural log of okay, I should read it differently. If a and b are both greater than 0 and a is less than b, then the natural log of a is less than the natural log of b. Well, that's true. If a is less than b, then natural log of a is less than the natural log of b. And they just added in that 0 thing because you can take natural logarithms of complex and negative numbers actually, but again, for the sake of this review, don't worry about that. So yeah, I mean, I guess if you just really think about it, I'm not really sure how else to explain it. It's just, if you've got a smaller number in here like 2, right, and a bigger number in here like 3, well, this is saying e to what power gives you 2 and e to what power gives you 3. Well, you're going to have to raise e to a bigger power to get 3 than you are to get 2. So that's the reason why this property is true. Number 9, if x is greater than 0, and again, they just have the greater than 0 thing because exponentiation is always positive under the real numbers, then the natural log of x, and this is important, I think I made this distinction, but maybe I forgot. The natural log of x, and this whole quantity is being raised to the 6th. And they're claiming that this is equal to 6 times the natural log of x. This is false. This is not true. I think I set it up here somewhere. Oh yeah, right here. Right. This property only holds when the power is within the input. This is not within the input. This is an exponent to the whole thing. But right here, this is the input, this x here. If it was x to the 6th, it would work, but it's the natural log of x. And the whole quantity is raised to the 6th. So, no, that is not true. Okay. Oh, this one probably. If x is greater than 0 and a is greater than 1, okay, then the natural log of x divided by the natural log of a is equal to the natural log of x over a. No, that's false. If it were the natural log of x minus the natural log of a, right, but then by this property it is true, but that's false. Okay, tangent inverse of -1, oh, okay, tangent inverse of -1, and by the way, I hate the tangent inverse notation. I'm never going to use it. I'm always going to use arctan. Only because I think some people, it's confusing. Like with the f inverse notation, people might think you're raising it to the -1. So I'm always going to use arctan. So they're claiming that arctan of -1 is equal to 3 pi over 4. So what is arctan of x? Arctan of x is, you plug in an angle and you get a number. No, I'm sorry, I mixed that up. You plug in okay, if you want cosine of x, right, what do? You plug in an angle, say pi over 4, and you get a number, square root of 2 over 2, right? If you want arc cosine, right, you plug in a number and you get an angle. So they're inverses of each other, basically. So you have to imagine the unit circle in your head, right? You got 0, you got pi over 4, you got 2 pi over 4, and you got 3 pi over 4. So 3 here. I'm guess I'm scrunched for room. So 3 pi over 4, right? If this is, that's a no, that's a horrible circle. I have to at least make them look decent. All right, so 3 pi over 4, right, is something, it's like 45 degrees from this reference here. Okay. So, and at all multiples of pi over 4, right, here, these 4 points here, right, this point here, 45 degrees pi over 4 is square root 2 over 2, comma, square root 2 over 2. This point here is the same as this point here, right, because it's just reflected over the y-axis, but since you reflected over the y-axis, the x-coordinate is negative. So this point here at 3 pi over 4 is negative square root 2 over 2, comma, square root 2 over 2. And if you remember, right, cosine is your x-coordinate. Yeah, cosine is your x-coordinate. And sine is your y-coordinate, so, you know, just divide square root 2 over 2 by negative square root 2 over 2, right? Because sine of x over cosine x is tangent x. So when you divide square root 2 over 2 by negative square root 2 over 2, right? That's just, these are the same except for a negative sign. You can put that out there. That's negative 1 because this is 1. Okay, that's negative 1. So, and that happened at 3 pi over 4. So yes, that is true. Okay, tangent inverse of x is equal to sine inverse of x over cosine inverse of x. This is false. Why? So, okay. Hopefully, maybe, I think Miss Brzezicki did it last year, I'm not sure. But, if you remember the restricted ranges for the arc trig functions, then what? Then, oh, so, sine, and the way I remember it is, great, if you've got sine of x is something like that. So when you reflect it over line y equals x, you're gonna get something like that-ish. So the restricted range of arcsine is from negative pi over 2 to pi over 2, and the restricted range from cosine is from 0 to pi. So in other words, since the restricted ranges aren't the same, if you plug in a number that is within the restricted range of one and not within the restricted range of another, then this will give you a false answer, and you can plug that in for yourself and see. But so 12 is false, and again, you can plug in numbers if you want and see. But that's kind of that's one of the reasons why it's false. There's more. If x is any real number, then the square root of x squared is equal to x. This is not true. Not true. The square root of x squared is equal to plus or minus x. Plus or minus x. Right, the way you could see this is, let x be negative 3, for example. The square root of negative 3 squared is equal to the square root of 9 is equal to 3. Right, but 3 is not equal. I should write that down instead of fooling around with my pen. Let x be equal to negative 3. Square root of negative 3 squared is equal to the square root of 9, which is equal to 3. But 3 is not equal to negative 3, right? 3 is equal to plus or minus 3, right, when you take the positive version. So, in other words, when you have when you put a plus or minus basically on this x here, you put a plus or minus when you have an even power. Oh, I shouldn't put a comma there. Even power, even index, and an odd resulting power. So what do I mean by this? Well, okay. For example, right, if you have this square root, I'm sorry, if you have the cube root of x cubed, let x be negative 2, for example. The negative 2 cubed is negative 2 times negative 2 times negative 2, which is negative 8. And the cube root of negative 8 is what number multiplied by itself 3 times gives you negative 8. Well, it's negative 2. We just did that here. So this is equal to negative 2. And no, you don't need to put a plus or minus here, right? It's one answer. And again, you have, the reason why you don't need to put a plus or minus is like what I said from right here. You have an odd index, right? You have an odd power, and you have, this is really -2 to 1. You have a odd power, but not all three of those are true, so you don't need to do that. Okay. Okay, that's the true and false. Wow, this is taking a lot longer than I thought. I guess people probably spend a good bit of time on this. Oh, wow. Let's see. I want to see what... okay. I might just... I'm not sure what I'm gonna... I might... I think really most people know this. So. I guess I'll just go through a couple other... Oh, I remember some people asking me about how to tell if the inverse of a function is actually a function or not. So let's pick a function, say x squared. It looks something like that, right? F of x is equal to x squared is not 1-to-1 or injective. In other words, it takes on the same, for a given x value, you can get, oh, I've butchered this, okay. In other words, okay, if a function is 1-to-1, then what f of, if let's say you pick a given x value, say x1, f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Okay, let's pick a different function. I think it'll be a little easier to illustrate. Square root of x. Oh, this is really plus or minus square root of x. Right, so if you plug in, say, x is equal to 2. No, let's do 4 because that's a nicer number. 4, you can either get 2 or you can get -2 down there. So in other words, f of x is equal to plus or minus square root of x is not 1-to-1 or injective, or it doesn't, in other words, for a given x value, it can take on multiple y values. So, a way you can test whether a given function, whether a function's inverse is actually a function, is you take the original function. So let's take f of x, right? Okay. Well, in order to test that, you know, the function that you're actually dealing with is a function itself, then you'll use the vertical line test. So in other words, right, you'll take vertical lines and see if it only intersects the graph at one point, and it does at every vertical line, right? So this is a function. Now, but if you wanted to see if the inverse of x squared, which is this, plus or minus square root of x, and you can see because it's reflected over y equals x. If you want to see whether this was a function, right, what you're doing is you're going like this. So you're reflecting it over y equals x, so all those vertical lines become horizontal lines. So rather than actually finding the, well, you can find the inverse function and then use the vertical line test on the actual inverse function. Or you can be lazy like most mathematicians, and you can just take a horizontal line, since you're reflecting it over y equals x, of your original function. And then if a horizontal line intersects the graph at more than one point, then its inverse will not be a function. Okay. Oh, I guess another important, I just was flipping through the pages, another important logarithm property that you might want to know is a to the log base b of c is equal to c to the log base b of a. So for example, 2 to the log base 3 of 5 is equal to 5 to the log base 3 of 2. I'm going to leave the proof to you all if you really are interested in proof. but my suggestion would be switch the 2 and the 5 to E. All right, we like base E. Base E works out nice. Okay. I am gonna go again, but I'm gonna finish recording some more later. So I will see you later.